Now beginning Unit 3, talking about intermolecular forces. So far, what we've been talking about in the last unit were intramolecular forces, the actual like bonds themselves, ionic bonds, the covalent bond sharing of electrons, metallic bonding. Those are all intra forces, and they are considered, much stronger than intermolecular forces, which are going to be between molecules. And there's some examples here on this beginning slide showing you some London dispersion and some dipole forces here. Now for the learning targets and enduring understanding. Intermolecular forces can explain the physical properties of a material. So that's going to be throughout a lot of the unit. So after this is over, you should be able to identify the intermolecular force for different molecules, explain their IMFs' roles in determining the physical properties, explain how the IMFs determine phases of matter, and compare relative strengths of IMFs based on property data given, Let's start with talking about states of matter, because really the fundamental difference between the states of matter or phases of matter has to do with the distance between the particles. And I particularly really like this example, this picture example here, because it's the halogen group, because we've got chlorine, we've got bromine, and we have iodine. Of course, they're an interesting group because throughout the group, yes, they're all diatomic, but also we have two gases, a liquid and a solid. So their phases definitely vary in this particular group. Fluorine is also a gas at normal conditions, which we would consider room temperature and like standard pressure, the pressure of the atmosphere at sea level. But as you can see, chlorine is this yellow-green gas, and it fills up the flask here. And the particles are spaced far apart here for a gas. And they have complete random motion bouncing off the walls of their container, exerting pressure on the walls of the container by, coming and colliding with the walls of the container. The liquid here, bromine liquid, is this brown orangey color. But as you can see, if you look at the molecular level here, the particles are much closer together. They still have the ability to move and rotate, and they have more freedom, but they are much, much closer together. And last but not least, our iodine crystals, the iodine crystals, they're quite interesting because they're even closer together, and they're of course packed together in a nice, I'd say crystalline packing, as you can see angled here, packing together. And they are in an ordered like pattern. The positions are fixed. Now that doesn't mean they don't move. They actually are vibrating and still possess kinetic energy, but they don't have random free motion like a gas, which has lots of kinetic energy, or even just the rotation ability and a little bit of the flipping that the liquid has, which is still like medium kinetic energy if we're looking at that. The solid is in fixed position with vibrational movement, but still has kinetic energy. The only time particles would not have kinetic energy at all is if we are at absolute zero, which is 0 Kelvin. And that's when all motion stops at that particular measurement. Now, going back to states of matter, the state of a substance is in at its particular temperature and pressure depends on two antagonistic entities. So these are opposing entities. The kinetic energy I was just talking about, how fast are the particles moving, and the strength of the forces between the particles. So the stronger forces mean less movement. So opposing factors here. Less forces means more movement. So keep that in mind. They are opposing ideas here, opposing properties. Now here's a good table that shows you the basics here. And describing the characteristics of gases, liquid, and solids and their properties. The gas assumes both the volume and shape of the container. That's where we say it fills the container completely. So it's just going to be in constant random motion bouncing off the walls of the container. Diffusion is very rapid. It is compressible because there's a lot of space between those particles. Liquids, they assume the shape of their container. They do not expand to fill it though. And they do not have the ability to be, it's virtually incompressible because the particles are much closer together. Does flow readily though, because, has some flowing ability because the particles do have the ability to move. And diffusion is slower than it would be in a gas. But like if you've ever taken food coloring and like put it in a glass of water, you can watch it diffuse. It still diffuses, faster than it would be if you were trying to put it in a solid. Solids, we say, have definite shape and volume. They are obviously not going to fill a container because they already have their own shape and volume. Also not compressible or incompressible because the spaces between the particles are really close, does not flow, and it's extremely slow. So if you ever took like a cube, like a potato cube, and put some dye on that, you can watch it diffuse, but it would be more slow than it would if you were to put it in, let's say, a glass of water. Intermolecular forces, or IMFs. Want to make sure that we have the idea here, inter prefix, that means between, right? Between, whereas intra prefix means within. So if we're looking here, this bond right here is the actual covalent bond. It's a polar bond. It's the sharing of electrons. Okay, that's going to be your intra force. Ionic bonds are also considered intra-forces. The metallic bonds are considered intra-forces. So they're within the substance itself. Now, ionic and metallic form those lattices and those crystalline patterns and whatever, and that's because they're like a repeating positive, negative sea of electrons deal separate, different kind of idea. However, for molecules, covalent compounds, that's where we're really focusing on for IMFs, covalent compounds, because it's going to be between molecules. So this dotted line here is showing you the IMF, this weak intermolecular attraction. It's between two molecules of HCl here. And what you're seeing here is it actually is forming an attractive force because this side of the chlorine is partially negative. This side over here by the hydrogen is partially positive. These partial charges are still Coulombic forces because it's positives and negatives attracting, but because they're only partial charges, they're very weak, especially if you're, trying to compare it to something ionic like NaCl, where there's a full charge, that electrostatic attraction. So different, definitely in terms of strength. Ionic, way stronger than anything that would be considered intermolecular. So those attractions are going to be the ones that are between molecules, IMF. The inter ones are going to be the covalent bonds within the molecule, not to confuse those two factors. These intermolecular attractions are, however, strong enough to control physical properties such as boiling points, melting points, vapor pressures, and viscosities. So even though they're weak, they do play a role in establishing these properties for these different substances. And we have to be able to compare like certain physical properties, like the forces in chlorine are weaker than the forces in bromine because, chlorine exists as a gas at normal conditions, whereas bromine is a liquid. So the forces are stronger in bromine. I know that just based off of the phases of the matter because it pulls the particles closer in order to be the liquid. So even though these are weaker forces, say in comparison to NaCl or an ionic compound, they do still control the physical properties of these molecules, some of the molecular solids or even the molecules that are gases or liquids at normal conditions. One other thing I wanted to point out, even though this is not really an AP thing, but if you do research and look around and see things on the internet, you might see intermolecular forces referred to as van der Waals forces. It's just another term, but if you're, looking through your book or looking through online, you might see that term, and it really is just pretty much synonymous with intermolecular forces. Those van der Waals forces would be also another way of saying that. Now we're going to go over the three types. We're going to start with London dispersion because they are the weakest, but probably coming back to you now, London dispersion, dipole-dipole, or hydrogen bonding. Now, some people abbreviate London dispersion with LDFs. You can call them that, or you could simply just call them dispersion forces. That's all. That also works. And sometimes they'd call them dipole-dipole forces. You can do that as well. Hydrogen bonding, of course, it's kind of its own class. Now, London dispersion forces. They're forces of attractions between temporary instantaneous dipoles. So these are created based off of the conditions that they're in. They are considered the weakest of all the IMFs, pretty much of all the forces, because, you know, IMFs in general are weaker than the other ones, but this is the weakest of the IMFs. Now, all atoms, so when I say all atoms here, I'm referring to the noble gases, because noble gases a lot of them don't form compounds. Like xenon pretty much is the only one that does. I guess krypton can form a few compounds, but for the most part, like helium, neon, argon don't form compounds. They still have electron clouds though. So anything with an electron cloud can do dispersion forces. So when we say, those are the few exceptions there when we say atoms, because we're talking about helium, neon, and argon engaging in London dispersion forces. But we're really mostly going to be looking at molecules. So these are covalent compounds already. What you see here is, you know, it's really about the placement of the atom or molecule where the electron cloud is. So if we're looking here, this is bromine, diatomic bromine. And if it's in and of itself, existing by itself, it's very symmetrical and nonpolar. There are no dipole moments, okay? However, you put two bromines next to each other, well, their electron clouds are going to interact with one another, and we know electrons repel other electrons. So it creates a temporary instantaneous dipole, induced dipole, another way to say that. And then it becomes asymmetrical, resulting in this temporary dipole that creates these very weak partial charges. They are positive and negative partial Coulombic charges, though, that will attract. So it forms this weak attractive force between neighboring molecules. Or atoms if we're talking like neon to neon. Like for instance, in this particular example, we're looking at helium, and helium is very small like hydrogen. It only has this 1s orbital, and it only has 2 electrons in the 1s orbital. And for the most part, the electrons, you know, stay far away from each other, they repel each other, but it does occasionally happen where they do end up on the same side of the atom. And when that occurs, something like this will happen. See how they've migrated over here together on that side of the atom. Now this, though, when they do that, this part is partially negative. And if they're near a neighboring atom, that is also going to cause electrons here to repel and go the other side away from them. And it also would attract to the positive protons in the nucleus. So you got a couple of attractive forces and repulsive forces working together to create these induced dipoles. And so basically by being next to a neighboring electron cloud, it creates these very weak partial charges. And we do call them induced dipoles. This would be more of the instantaneous, where just randomly the electrons ended up on the same side, so it's an instantaneous dipole. And if it's near another atom and creating a dipole, then it would be inducing a dipole of a neighboring atom there. So like atom B for helium is now inducing a dipole in atom A. So as you can see here, these electrons now on this side start attracting to the nucleus over here, and it also repels these electrons to go to the other side of the cloud, and this becomes the partial negative, and this side is the partial positive, and it creates these partial charges, these dipole ends that now have the possibility of attracting to an opposite partial negative charge. Like this one's the positive, so it's going to attract to the partial negative due to that fact. Now, London dispersion forces are attractions between instantaneous and induced dipoles. And all of these forces, of course, are present in anything with an electron cloud. So even water that we know is polar and has hydrogen bonding, it also has London dispersion forces. So it's the bottom of the rung. Everything with an electron cloud possesses London dispersion forces. Now this is a key term that we're going to have to really get used to using. The tendency of an electron cloud to distort in this way where it goes to one side and it creates the dipole. It's called polarizability. If your cloud is more polarizable, it creates a bigger dipole and it creates a stronger intermolecular force. This term is very important, especially when you're trying to explain and compare strengths of forces. Which one has a more polarizable cloud? And we're going to talk about what features come along with that, but the more polarizable clouds usually create bigger dipoles, create bigger partial charges, and therefore are stronger. So we're going to be referring and using that term quite a lot when we're differentiating between intermolecular forces. And that's a term they expect to see in your free responses, when you're trying to explain them and compare them. All right, last year or in Chem 1, we used molecular weight kind of as a metric to gauge London dispersion forces. The more weight, the stronger the dispersion forces. Well, why is that exactly? It's not really because of the weight. We don't really care about the neutrons and protons in here. Really, what goes along with the weight? If it's a heavier atom or a heavier molecule, that means it has more electrons too that accompany the weight. And if you have more electrons, okay, they have larger electron clouds, they have the capability of becoming polarized. And it's more polarizable, and you can create a bigger dipole if you have a bigger electron cloud that contains more electrons. So if you're looking here at the boiling points of the different, here they have the noble gases on the chart here. So you can see those boiling points are pretty low. They're all in the negative Celsius. These are all in K. So remember, that's just 27 is a little bit above absolute zero. That's really, really a low boiling point. Neon is. But you start to look at things that are getting bigger here, especially iodine. Iodine we know is a solid at room temperature. It's 485 K, so that's, subtract 273 from that and you know the Celsius. But stronger forces, because iodine is way more massive. It has, let's see here, I'm looking at my periodic table. Iodine has 106 electrons in its cloud because it's 53 times 2. It has 53 to start with. So 106 electrons in its cloud. So that's a much more polarizable cloud than, say, neon, which only has 10 electrons. And that ability is, of course, going to make it have a much higher boiling point because the forces will be stronger in terms of those dispersion forces. Another factor that's very important here that we need to look at, because it's not just the size of the cloud that matters. We also have to look at the shape and the orientation and the branching patterns. Things that are molecules that are long and skinny, they're more like linear shape. They have stronger dispersion forces because their cloud is more polarizable and they have more surface area to shift across. So long, skinny molecules based off of their shape typically have higher dispersion forces than ones that are little short, fat ones. So the arrangement here, although these are both C5H12, N-pentane is just 5 carbons in a row, whereas here, as you can see, they're more branched together and they form more of like a blob-like structure. But makes a difference in the boiling point. This one's 282, whereas this one's 309. So being more linear in shape, long and skinny, definitely leads to a more polarizable cloud.